Hey everyone! Welcome back to Chem Story. Today we're diving into organic halogen compounds, molecules where a halogen like fluorine, chlorine, bromine, or iodine is bonded to carbon. You'll find them everywhere, in reactions, pharmaceuticals, plastics, and more. They're super versatile, and they play a big role in chemistry. So, let's take a closer look and see what makes them so interesting. Let's start with alkyl halides, or haloalkanes. Here, the halogen is bonded to an sp3 hybridized carbon, which just means it's part of a regular alkane. Their general formula is Rx, where X is the halogen. What makes them so useful is their reactivity. The CX bond is polar, so the carbon becomes slightly positive, and that makes it a perfect target for nucleophiles. That's why alkyl halides go through substitution reactions, where the halogen gets replaced. Depending on the conditions, they can also go through elimination, forming alkenes. Since halogens are great leaving groups, these compounds can be easily turned into alcohols, amines, ethers, and more. That's what makes them such important building blocks in organic chemistry. Alright, now let's look at alkyl halides, also called haloalkenes. In these compounds, the halogen is attached to an sp2 hybridized carbon in a double bond. Unlike alkyl halides, they don't really do substitution. The CX bond is stronger, and the pi system blocks the SN2 backside attack. A common example is vinyl chloride, used to make PVC, one of the most widely used plastics. They also take part in palladium-catalyzed reactions, like the Heck reaction, where they form new carbon-carbon bonds. So even if they're not super reactive in substitution, they're still really useful in synthesis. Next up, alkyl halides, or haloalkynes. Here, the halogen is bonded to an sp hybridized carbon, which makes the molecule linear and pretty reactive. That's because sp carbons are more electronegative, and the triple bond pulls electron density away, making the whole system electron poor. One key reaction is the Sonogashira coupling. It links an alkyl halide with an aryl or vinyl halide to form a carbon-carbon bond. The result is a nice conjugated system, super useful for building complex molecules. Now let's talk about aryl halides, or haloarenes. These have a halogen bonded to an sp2 hybridized carbon in an aromatic ring, like benzene. They don't really do substitution reactions like alkyl halides. The CX bond is strong, and the delocalized pi system blocks SN2 attacks. But under harsh conditions, like high heat, or with strong electron withdrawing groups at the ortho or para positions, SNAR reactions can happen. Aryl halides are also key players in cross-coupling reactions, like Suzuki and Heck, which are great for forming new carbon-carbon bonds in synthesis. Next, let's look at acyl halides, also called acid halides. They have a halogen attached to a carbonyl carbon. Because both the halogen and the carbonyl group are electron withdrawing, the carbon becomes super electrophilic. That makes it easy for nucleophiles to attack. A common example is acetyl chloride, CH3COCl. It reacts fast, which is why acyl halides are great intermediates for making esters, amides, and other acid derivatives. They're too reactive to use directly in most products, but perfect for synthesis steps. Finally, let's talk about allylic and benzylic halides. In these, the halogen is bonded to an sp3 carbon that's right next to a double bond or an aromatic ring. Technically, they're alkyl halides, but they're way more reactive. Why? Two reasons. First, the carbocat ion formed after the halide leaves is stabilized by resonance. Second, the nearby pi system lowers the activation energy during the reaction. That makes substitution and elimination much easier. Among all the types we've seen, alkyl halides are the real backbone of organic chemistry. You'll see them again and again in countless reactions. And to see why they're so central, we need to take a closer look at the CX bond. To understand their reactivity, let's look at the CX bond and its dipole moment. Since halogens are more electronegative than carbon, they pull electrons toward themselves, creating a polar bond. That gives us a dipole moment, mu, with a partial positive charge on carbon, delta plus, and a partial negative on the halogen, delta minus. This makes the carbon electrophilic and an easy target for nucleophiles. That's the key to substitution reactions in alkyl halides. Now let's break down the dipole moment a bit more. It's a vector that points from the positive carbon to the negative halogen, and it's calculated as mu equals Q times R. Here, Q is the charge separation, and R is the bond length. As you go down the halogen group from fluorine to iodine, electronegativity decreases, so Q gets smaller, but bond length, R, increases. Since dipole moment depends on both, the trend isn't linear. You need to consider both charge and distance. Let's look at some actual dipole moment values using CH3X compounds. CCl has the highest at 1.56 dB, followed by CF at 1.51, CBr at 1.48, and Ci at 1.29. You might expect CF to be the strongest, and it is, in terms of charge separation, but the CF bond is short, so the overall dipole moment stays lower. CCl has a bit less charge separation, but a longer bond, which gives it the biggest dipole overall. So the trend comes from both electronegativity and bond length. Now let's talk about boiling and melting points of alkyl halides. Compared to similar alkanes, they usually boil at higher temperatures. That's because halogens bring stronger intermolecular forces, especially dipole-dipole interactions, and stronger dispersion forces. For example, 1-chloropentane boils at 108 degrees Celsius, while heptane, with similar mass, boils at just 98 degrees. That extra polarity from the CX bond makes the difference. What happens when the alkyl chain gets longer? Both boiling and melting points go up. Longer chains mean more surface area and higher molecular weight, which leads to stronger dispersion forces. So if you compare a small bromoalkane to a larger one, the bigger one always boils and melts at a higher temperature. Simple rule: bigger molecules stick together more. We see a similar trend with different halogens. As you go from chlorine to bromine to iodine, boiling and melting points increase. That's because heavier halogens have more mass and are more polarizable, which strengthens dispersion forces and makes intermolecular interactions stronger. So just like with longer chains, heavier halogens mean higher boiling and melting points. Now let's talk about density. Most organic compounds float on water, but many halogenated ones, like CH2Cl2, CHCl3, and CCl4, actually sink. Why? Because halogens are heavy. When a molecule has multiple halogens, its density goes way up. Water's density is about 1.0 grams per milliliter. Chloroform is around 1.49, and carbon tetrachloride is about 1.59. That's why these solvents settle at the bottom in liquid-liquid extractions. Good to remember in the lab. Let's wrap up with solubility. Alkyl halides are mildly polar. Not enough to mix with water, but perfect for organic solvents. They can't hydrogen bond, and their dipole isn't strong enough for water. But in solvents like ether, benzene, or chloroform, they dissolve easily. That's one reason they're so widely used in organic reactions and industrial processes. Alright, that's our overview of organic halogen compounds. We looked at their types, properties, and reactivity, and saw why alkyl halides are such key building blocks. In the next lesson, we'll talk about how to make them the key reactions that form alkyl halides. So stick around, and I'll see you in the next one.